If any of you are watching, I am loading OpenSpace. I am Carter Emmard. I'm the Director of Astrovisualization for the American Museum of Natural History. We're about to see OpenSpace. I think I'm still 2 minutes shy, or a minute shy now of going on, but that'll be occupying the screen in a second. And we're doing this in coordination with so our booth here at LPSC, along with the innovative display company Illuminati, who we've worked with over the years to help bring what we do at the museum to the public at large, not just at a few select museums and planetariums, but portables and solutions that go out worldwide. And so Illuminati has been a leader in this field, creating a whole range of products. And our latest software is we've had a series. Is OpenSpace. I'm going to add him in here from the Illuminati. Hello, Adam. Hello, sir.
Hello, we are all set to go.
Excellent. I'm already streaming, so I'm not sure whether I'm up or not. I started talking a little bit.
You are. You're good to go.
Excellent. So I'll just keep talking. I want to focus on the ISS for a moment. This interactive software is really a visualization of the entire universe. I'll show you that in a moment. But
I do see a question on the board, but I do believe it's because it is the Illuminati that is live streaming this. But our question is, could you share the ultimate truth?
Could I share the ultimate truth?
I believe it's playing into our play on words with the Illuminati, Carter.
Exactly. So yeah, well, I'd love to talk about the ultimate truth because essentially we're showing science, and it's of what we can resolve of the ultimate truth. Let's put it that way.
All right. Well, if we see any additional questions come in, I'll let you know.
So as I line up here let's see, get up close and personal to the data, there's a number of things happening as I'm interacting. I'm using a 3-button mouse here in this OpenSpace software, and to properly introduce it, what I wanted to do is I'm sharing my menus, which I never do in presentation modes, other than this is demo mode, and so it's sort of showing all this. I'm centered on the International Space Station. It's the only orbit I'm showing currently. I could show more with other satellites. I'll do that in a little bit. But what I'm going to do is just go into Earth, select amongst layers, and what I want to do is prioritize a layer we're looking at yesterday. And why is that happening? Interesting. Let's see. I thought it was running. Let me check something. Okay. Yeah, actually, I should be able to zoom in on this and not have it go away. Possibly, I'm waiting. Waiting on the internet, which is, I've been running in a sort of cached mode for the demands of rapid fire presentations that we've been doing. I just did one that was a half hour, and I don't know why I'm sort of getting screwed here by coming in on this. I should be able to see data. Oh boy, every time I try to give it a whirl to actually be live. I've been having some issues. Okay, let me start at the top. Bad start today, sorry. OpenSpace is an interactive data visualization display. It is supported by NASA's Science Mission Directorate, of course, which has the major divisions of science for all of NASA, namely geoscience, Earth, helioscience, sun and planetary science. Well, we're all gathered at this conference, and then astrophysics beyond. And we really show that realm. OpenSpace began as a visualizer for what we call our digital universe, which is a catalog of all astronomical catalogs that we've sort of brought together into one source that are beyond the Milky Way. When we get, I'm sorry, beyond the solar system. When we get into the solar system, we get into dynamics and the need to have an ephemeris generation system. So we're using that of NASA, and their ephemeris generation it applies in sort of multiple, or it appears in multiple ways. The NAIF SPICE system for plotting not only planetary and small bodies throughout the solar system, but also mission trajectories and so on. We can show two-line elements for satellites. I kind of showed that just briefly as I was trying to get close to the International Space Station, but then my Earth map wasn't showing up. And so we can plot two-line elements, which we source. Actually, let me focus on Earth. I'll run the satellites here. I'll amp up time a bit. It's about 5 minutes per second, I believe. I can check that. Just bring up my menus. Oh, that's 30 minutes per second. So let's make that go to a little more stately pace. So the maps of Earth are being gathered. I was just being frustrated because for some reason, coming in closer, I had cached certain maps. So I was getting closer. I wasn't getting my data report on from NASA's Global Imagery Browse Service. What I'm going to do, allow me to actually step back a day or two. So let's see. I'll go back to the 16th. We also have a multicolored map that we briefly saw there that might just suddenly flash up. This is the international date line showing a discontinuity in clouds because this is gathered as a mosaic from low Earth orbit that stitches together sections or gores to make up the entire Earth over a course of 24 hours. I'm going to open my image layers, call them color layers here. I'm going to turn off cloud height colorized and just see for, in the case of the 16th, I should be able to get in closer. And, oh boy, why is this happening? Don't understand. Okay, well, it should be reading in the data. I've expressly told it not to just run off the cache. I'm sorry that I'm just getting into a complex description of things. So OpenSpace is an academic collaboration between the American Museum of Natural History in New York, Sweden's Linköping University, who we've collaborated with for 20 years now. They're world's leader in data visualization research. The University of Utah's Scientific Computing and Imaging Institute, and New York University's Tan Dun School of Engineering. And the idea is to basically create an experience of the universe across all scales by applying latest graphics technology. So think of gaming engine, but applied to data visualization. The Earth we see makes use of latest maps, or in the case of where I was getting frustrated, maybe not. I'm not sure if there is a problem server side or not. But I'll avoid that for the moment. But we have an atmosphere that we apply, which is a physics-based Rayleigh and me scattering atmosphere. OpenSpace is an academic collaboration, and that's being developed both by professional developers, of which we have about half a dozen, and but also students from Linköping University in Sweden, where they are schooled in a program of media technologies. And in the case of the students that we get are majoring within data visualization, advanced computer graphics. And so they have typically bite off projects where we're trying to innovate new solutions. So various parts of OpenSpace have sort of been built as student projects, as master's thesis projects, and published. Our website is openspaceproject.com. We're really a .org, but anyway, it's openspaceproject.com. You can download the software freely for Windows, for Mac. You can compile it in Linux. There's also a wiki, YouTube site, and we have a GitHub site. The wiki actually references the academic papers upon which the software is built. Let's pull out a little bit and just give you an example of the scale range of OpenSpace before I come back and focus on some planetary science. So, for example, if I come up and just look at how OpenSpace is organized, solar system, Milky Way, universe, there are grids and things like this under the other label, and then shortcuts. Fine. Within the Milky Way, addressing something as simple as, say, constellations, I could open up the menus or I can search. So in this case, let's turn on the constellations as stick figures. Star-to-star connection. We also have Constellation Art, thanks to a colleague of ours and CCNY, who's actually drawn the constellations himself, James Hedberg. Let me see if I could actually bring those up for a moment. Do constellation. Let's do the Orion image, for example. And so he's actually gone in and drawn this, which is actually quite nice. He's drawn all constellations, 88 constellations or so. And so let's pull out. We see the lunar orbit. You see the inner solar system. When we get out here, we can plot various small bodies. So let me just see if I've, in fact, loaded that. Open up my solar system. Small bodies. And let's load, for example, the Apollo asteroids. Let's load the outer main asteroid belt. Okay, and get closer to see that. I'm running this off of an Alienware laptop of a few years old vintage. I can actually get a read on my frame rate. I'm down to 11 frames a second. And that's primarily because I've brought up several thousand points. And I've not just brought them up as points, they're actually subject to time. So if I amp time up here just a little bit, we'll start to see them move. So the CPU is calculating these, the GPU has to display them. So I'm challenging my laptop here, but suffice to say that OpenSpace runs on graphics card technology. And so we do not have a purview of this for just running off, say, a website. So this is currently a download with a need for a good graphics card. Coming up, and if I turn off the main asteroids and just leave the Apollo asteroids, I'm still at kind of a low frame rate. Let's turn those off. And see that we'll probably pick back up to, okay, about 75 frames per second. Fine. Let me come out of the solar system. I'm going to, I'll leave Orion in this field of view, and as I pull out, we're going to, as we move away from the solar system, we're going to bring up the true brightness of the sun in comparison to other stars. And the star should be coming in from the lower left in a moment. Let's see, there. Is Alpha Centauri, just below the sun, but we already see three-dimensionally the bright stars Sirius and Procyon. Notice how Orion, which the artwork has been frozen at about 10 light years away, that most of the stars of Orion are farther than that. The belt stars and the Orion Nebula and the Sword are on the order of about 500 parsecs, between 1,000 and 2,000 light years. So, and now we see the star-to-star connection. Other data layers that can be brought into this visualization. Let me actually turn off the readout. I had opened the solar system. I had the Milky Way open here. If we explore exoplanets, I can turn on the dynamically discovered exoplanets. I could turn on their labels, but suffice to say, I'll just leave that on. I'm going to turn on the Kepler results. And we can see a few of the Kepler results after they lost their reaction wheels. But I wanted to roll around so that we see the main belt or footprint of the Kepler primary mission, where you can see the footprints of the detectors and the stars that were detected to have planets. So they move out. Okay, fine. Now we're in the kind of abstract visualization in 3D of all this data. You might ask, well, how far away is the sun? How far are we in this visualization? So let me close the Milky Way. I'm going to go into the grids I spoke of briefly before. I'm just going to turn on a sphere that shows the extent of our radio signals that have reached out. This is currently about 85 light years in radius, or the first signals to leave Earth about 85 years ago, with increased broadcast strength in radio to make it beyond the ionosphere, and then radars followed by TV carrier wave. And so this gives us a bit of a sense of within the sphere what planets that have been identified, sort of within that range, broadcast range of Earth, so far at least. And I'll leave this on to pull out, and we see the Milky Way is sort of transitioning here to that of a model. This is a constrained simulation of the Milky Way. Thanks to our colleagues at the National Observatory in Japan and Tokyo University, Baba, Wada, and Saito, a paper on this about a decade ago, which we used we visualized actually for one of our space show productions at the American Museum of Natural History, Hayden Planetarium, and called Dark Universe. So we needed a good Milky Way simulation. It has stars and gas components, but allow me just for a moment while I'm here, just looking at my time. So I think I have enough time to show this. Within the Milky Way database, again, I can turn on OB associations, mapping out pretty much where the primary spiral arms are around us. For example, I'm turning on planetary nebulae, and they're somewhat dominated by the stars that we're seeing here in the model. So let me actually call that and open that up. I'm going to turn off the star rendering and the volumes. I didn't mean to turn that off. I was going to try to make it brighter, but suffice to say, if I move out, we start to blend that also with an image of NGC 1232, a galaxy that we know is similar to Milky Way. So then I'll turn on globular star clusters, which inhabit the halo of the Milky Way. So in this way, these data sets actually sort of map out our galaxy. And then beyond that, well, we see the Magellanic Clouds sort of ghosting in to the lower right. And as I pull out, we'll now be fading up galaxy databases here. Actually, let me stop time. I was cruising along here. And now we are seeing basically a extragalactic database brought to us by Brent Tully from the University of Hawaii. Andromeda is this group right here. I can turn on labels. Let me try to do that for us. I'm going to close up the Milky Way group, open up the universe. I have galaxies as different surveys that we have here. We're going to see the Sloan in a moment. But let me just come down to the Tully galaxies and open them up. And I believe their labels are here. So yes, this maps out where you see the different data points identified. There's Andromeda, M101, M31, and 32. 32 is a little satellite galaxy along with M110. But also M33, the triangulum pinwheel galaxy. So if you studied astronomy at all, you know that this is really comprises our local group. There's some other smaller galaxies associated with us. But if I tip in this direction, we should start to see the Virgo cluster of galaxies often behind the center right now. And I believe we can see cursor on screen. So it's the cluster behind us, some 65 million light years away. And so representing the sort of highest gravitational potential in the region. So it's a gravitational infall to the heart of the Virgo supercluster. So about 30,000 galaxies out here that step us out to about 300 million light years before we then begin to fade on the Sloan survey. Now, if we had paid attention to actually the orientation of the Milky Way, we would have seen that these shadow areas in dark, lack of galaxies in the Sloan survey, are actually avoiding the Milky Way. So this is a zone of avoidance or the zone of obscuration of the Milky Way. And the Sloan was conducted from Apache Point in New Mexico. So above we see the northern view, and below we see as much of the southern sky that it covered. And we're seeing the large-scale structure of the universe here. Currently, where I am, we're looking out perhaps to about 2 billion light years in distance. Of course, using the Hubble relation of distance and recessional velocity from the expansion of the universe is giving us our distances. Using velocity as a distance metric gets a little bit screwed up in the case of a cluster of galaxies where peculiar velocities of just the galaxies orbiting the center of mass of the cluster. Some will be blue shifted and some will be red shifted. And so it complicates the distance metric seen here in these fingers of God that seem to point back at us. And then if I go farther out, we'll invoke finally beyond seeing the large-scale structure. When we get out into the quasar surveys, that structure is much less evident, but we're seeing very young galaxies in their formative process. Light has taken billions of years to get to us, the youngest objects that we see in the universe. And then finally, youngest light in the universe, surface of last scattering, the cosmic microwave background radiation imaged by the Planck satellite, co-registered with the other data sets here in what we call our Digital Universe 3D Atlas. And so with this, applying a radius with the expansion of the universe, some 42 billion light years, and then coming back through the Sloan survey on our way back home. let's go back in to look at some planetary science. So coming back home as we do through the galaxy surveys, every galaxy, of course, several 100 billion stars, perhaps 1 trillion planets. So a lot of planetary science to be had if we were to go out and visit all these places. But allow me to come back down now. I'm seeing, once again, different data groups. The yellowish pentagons are globular star clusters. Themselves tend to form this halo of the Milky Way off the disk, and then within the disk of star formation, we have the bright star regions, and also I'm seeing pulsars here, which I turned on, which are sort of the death remnants of some of the heavier stars. We would expect them to be in the disk, and once again, our radiosphere. There's a lot of data turned on right now. This is kind of a map that nobody, unless really studying it, it's too many map units to have on. I'll allow me to sort of pare some of that away. Tully naturally fades out, so I don't need to do that. Within my grids, I turned on our extent of the radiosphere, which is oriented in celestial coordinates. So actually, I'll keep it on for a second. If I come back down, we see the ecliptic plane of the solar system, to which, of course, the Earth is inclined 23.5 degrees. And am I going to embarrass myself? Oh, gosh, yes. In fact, the radiosphere was not positioned properly like the equatorial sphere. Now, what we're seeing is we can see the Little Dipper, the convergence up here is celestial north. The radiosphere, I believe, was actually oriented to that of the ecliptic, which is fine. Okay, going in a lot of detail about subject matter. Perhaps any of you watching probably don't care so much about astronomy. So let's come back down into closer to home. I will turn off some of these other data sets. Close up the galaxies, close up the universe, close up the grids, open up the solar system. I'll drink some water. Actually, Milky Way, I hadn't finished with that. So turn off the exoplanets. Turn off the globular clusters, and turn off the OB associations, planetary nebulae. Okay, fine. And I still have the Orion constellation turned on. We'll leave them on. So let's come back down nearer Earth, nearer to Earth. And I want to focus on the moon. And let's just see if I'm... okay, I'm going to first just manually focus on the moon. As we do, we select an object to pivot around. I went all the way out into deep space, but still I was pivoting around Earth. But as I now come up on the moon, actually with my time indicator, actually let me set that to now. Okay, and of course we're approaching first quarter moon. But what I'm going to do is just turn on basically a headlight to see the wide angle camera mosaic. No shading here involved currently. This is one of many different maps that I could show, but I'm going to come in to a prepared presentation just of the Apollo 17 landing site. So we work with other science activation groups. The Science Activation Program at NASA Science Mission Directorate is our funding, is a program to which we are attached. We are one of about a collective of 25 different groups selected for communicating outreach of science that NASA does. And so some of those groups are internal to NASA, such as NASA's TREX. So we can utilize maps from TREX. And also we collaborate with NASA's Eyes on the Solar System for some mission visualization results. But our data call, we also use most of the maps that are available from the U.S. Geological Survey. So as I come in now, what we've done is prepared a regional map. This is a map set by Haas et al. From acquired from the U.S. GS site. It's a collaboration with the German DLR on mapping Taurus Littrow. At 1 meter blended LROC imagery and also elevation mapping, but also insets of full resolution 25 centimeter. Let's come up to EVA 3 and to EVA station 6 here, and of course split rock coming down, rolling down North Massif, and look at some photogrammetry that we put in here from the Apollo Hasselblad photography. We can see that that the photogrammetry, of course, is only going to solve where it has enough coverage. The astronauts Jack Schmidt and Gene Cernan photographed enough coverage for us to use reality capture commercial software to basically do the photogrammetry solution, and they photograph the daylight side, of course. And but here we can come up quite close to the boulders, and in some cases we can see where samples were taken that, of course, are in the Lunar Receiving Lab. Let me just step out to, I like to come around here to show you have this much more consolidated sort of section of boulder or fragment 2. And then we start to see more vesicle structure. I think there's a contact here in this boulder. Get Jack Schmidt to comment further on that. There's fragment 3, smaller, and then fragments 4 and 5. And in this case, we can come up quite close and see inclusions, vesicles, and quite a lot of detail just in solving the photogrammetry. And then here in data-driven stories is really sort of put that in its proper place on the moon. Also, we can see Jack's footprints here, which is kind of novel. So anyway, in this case, we can look at these various things. Just to characterize the landing site a little more, we have, again, the elevation maps that apply. We're looking across, I believe, Henry Crater right now. And I'm going to target the lunar module, bring my, my interface back up, and just type in my keyword search, and I can focus on the limb. And, oh, geez, this happened again. Actually, the limb, because of the sequence in which I read in the height maps, the limb is not where it should be. It's up, so I'll just ignore that. We have a nice photogrammetry of the limb, but fine, let's just come in. Clearly, we can see within this nice map set what are rover trails versus footpaths on out to the Alsep station and beyond. And so we have done photogrammetry at the various station stops where, so we have photogrammetry for boulders at station 2 and station 6, 7, and 8, I believe. So let's move out now. I'd like to turn my attention to Venus for a second, and I hope that that works. I've been focusing on Mars. We'll go there in a second, but what I'd like to do is just call up Venus. And so I'll just type here, Venus. And so we'll go to Venus, and hopefully, because of this issue, I'm not certain why my Earth maps were not reading. I may have, I'm just wondering if I had actually saved my, let me just check something. Ooh, I see why now. I had corrected the script and forgot to save it. Boy, that was stupid. Anyway, with Venus, yeah, that's going to happen. Okay, that shouldn't be happening as I get close. This is partly because I just saved a cache really for Mars. I could get down close and personal to the map products for Venus, but that's not going to work with what I launched here. So my apologies on that. So we're looking at the SAR image results. We have global elevation. Of course, it's not that great, but we do have Robbie Herrick's best he could do with sort of stereo SAR image results, which is probably about maybe 25% of the surface. So I wish that I could just show you right now, and I'd have to do a reload. Suffice to say, let's go off to Mars. We actually have a lot of good coverage from Mercury. So there's Mars. It's sort of waiting for me to select it here. So we'll go off there. And as I do, let me just check in with Adam to see if there are any questions.
Not currently.
Oh, great. I'm doing a great job. Nobody's even asking any questions. So let's get up close and personal to Mars. And hopefully, I think this will probably work. As I do in these presentations, I've been approaching Mars to show that we use a color base layer as kind of a base template for Mars. You can see the atmosphere. We saw atmosphere on Earth. It's a physics-based Rayleigh and Mies scattering model. I don't currently have the models for Phobos and Deimos in here, but we have them and can put them in. So OpenSpace is our interactive tool, but I wear two hats at the Museum of Natural History. One is for directing our space show productions, where we will work for a year just in production on one topic for a 20-minute show, and putting a lot of data visualization into that. My lead technical director, John Parker, we really wanted the best color for Mars as possible. So what he did was to use the Mars Global Surveyor wide-angle camera mosaic, and then divide by a hillshade that matched basically the shading built into the images, and divide that out because we wanted to really just get kind of a Mars that was high sun and get color and tonality. You can see with Valles Marineris here it's lighter, and that's because we do have the elevation applied, and you can see that with the Tharsis Montes here. In fact, I'll just evolve time a little bit here. Allow me to do this for a second, and I will bring. Okay, I'm just going to. Let's see. I'll take that an hour further. So here we can see Olympus Mons sticking through the atmosphere, and the dark featuring of the volcanoes is apparent in imagery from our satellites around Mars, various missions, because they're sticking up through this thin atmosphere, and also the haze being much greater in the low-lying depths of the graben of Valles Marineris. So now let me turn on the Viking Mosaic, and that gets us down to perhaps 100 meters or so. I'm not exactly sure of the resolution of that, but it's in stark comparison to the global CTX mapping that has been shared with us from Murray Lab, Jay Dixon, there at Caltech Murray Lab. And he was very kind to share with us a beta result. And this is currently a work in progress. What I'm going to do is come up and invoke his his layer here. So once again, my image layers, so-called color layers, because potential for them being color. The Viking Mosaic, actually, if I turned off our global color, then you're seeing the color of the Viking Mosaic, but we're sort of replacing that with our color. And also the scattering in the atmosphere. And so we've been balancing the global color along with the color of the atmosphere from just purely the Rayleigh and me coefficients. Okay, and now I'm going to, let me turn off Viking. Once again, this is just our global color. You can see a little bit of the shadow details in there. I said that we worked hard to sort of get rid of. But now let me turn on the 5-meter global CTX. You'll notice immediately that there are contrast bands in at sort of equal sets of latitude. And that's sort of what made this sort of beta version that Jay shared with us. But let's come in a little closer. No vertical exaggeration being applied. And at this point, I'm stuttering a little bit. Oh, I turned off the Viking Mosaic. So usually if I fly too fast, it might stutter. So let me just try to come in here. I'm navigating with a 3-button mouse. It allows me to pivot, roll, orbit, and also descend or basically adjust range. And in this way, now I've sort of turned friction off, both in the radial direction as well as the sort of orbital navigation so that we can fly in. There's still constellations and orbit lines in the background. Maybe I'll turn the constellations off because it just gets annoying after a while. So, so turn those off. And in fact, what I'm going to do as well, I'll just show you that currently as we come through the atmosphere, we'll see the stars, which of course one wouldn't see. So I'll just call those up as well and turn those off. As I come in, let's just going back to the subject of what our layers are. I've got the global CTX, but I'm also turning on high-rise subset for the high-rise data that we have elevation for. That's one of the Magellanic clouds floating in the sky because I didn't turn off the Milky Way, which you'll also see up through the atmosphere there. As I come down into Western Candor, we're coming up on the 25 centimeter resolution high-rise of this particular area. So we see the predominance of these sulfate layers worked on by wind erosion. We can see sand dunes and pockets. And then we see, hills, yardangs sculptured by wind, and that they have elevations of, a few hundred meters at most. And whereas the background, this particular area is about 5,000 meters through the top of the canyon. And so in this way, especially in the native environment that this software was originally developed for, which is planetariums, you can explore and you can display it completely immersively around your eyesight. And so in a way, this is clearly, I know it's the closest to Mars I'll ever get, but also in a theater such as ours in New York with over 400 seats, it's a good way to take an audience with us to other worlds. We also have done local CTX enhancement. My high school students are running the NASA Ames stereo pipeline. So let's see how much I might improve the background. Now, I should say high school students, some former high school students, one of whom has a poster at LPSC. She's on her PhD track, Chiara Ferrari Long. Janie Levin, who's finishing up at Columbia, but going into planetary science. Not sure if she's selected her school yet. She impressed the faculty at Brown. She's also been co-authoring papers with Jay Dixon as he recruited her to help work in his projects out at Murray Lab the last couple of summers. Let's bring up my menus again here. I'm going to open up our height layers. People usually look at these menus and go, "Oh my gosh, that's a lot," but we just have a lot to call from, which is an embarrassment of riches. It's great. So let that data read in, and we may see basically this 200-meter MOLA HRSC map that we've been using is slowly sort of reading in here. It's reading in off disk. This Alienware laptop is doing a lot. We've been doing presentations all week. Let me clear out the menus. And I actually should get a better rendition of the canyon edge up here. Let's see if that increases better. Oh, just wondering if it should be under the purview of that particular data set. The mosaic of the CTX mosaic has elevation, as good as sort of 20-meter resolution. The terrain elevation for high-rise is about 1 meter, and sub-meter resolution for, of course, its images. And once again, no vertical exaggeration. In line with keeping the experiential elements, but with, guided by data visualization. The atmosphere here gives us kind of, a best guess at what this might actually look like, sans any particular meteorological phenomenon, hazes, things like that may be local or for that day. See a little bit of this Milky Way in the sky because I hadn't turned that off. And these layered features across SETI Mensa. Once again, I'm stuttering a little bit, which I don't like, but anyway, that's sort of what's happening. Melischasma, where we had, actually, I think I cached some of this. Very interesting, just in here, the gully systems that can be seen are quite compelling. Let's see if we've got some of that on disk, and I believe I do. And also, I could bring up some of the other high-rise. They would not be conforming to their own elevation. But suffice to say, I think I've made the point here. It's already about 20 after 3. Let me see if there are any questions. If not, perhaps I'll go to one of my favorite locations of vertical relief. Adam, are there any questions?
No questions, my friend, and I would suggest that we probably wrap up in the next 5 to 7 minutes.
Yeah, boy, I must be boring people to tears. So, if I am, if you're out there and I'm boring you,
you know how the last day of the conference gets. Everybody's tired.
Well, yeah, I wish I'd seen more of the conference, which I was registered for to see, but thanks to the era of remote conferences, I can watch either the prepared video talks or actually see the instant replays of some of the talks. So anyway, let me come down here on the Euphrates central mountain chain, and down in this particular area, I'd like to commend whoever it was that chose this particular spot as a target. So I come from a background in kind of a family tradition in artwork, and I tried to be a scientist, and I ended up as a visualizer. Some of my space painter colleagues, space artists, were fond of showing technical climbing, on Mars, and I thought, well, that seemed a little bit outrageous until I really saw this. And So I had cached this area. As I come in, the proximity is reading in the data. But there are some truly amazing areas in this particular exposed rock wall, and it was quite exciting. A lot of Mars, looks about as exciting as Iowa. I don't want to take anything away from Iowa if you come from there. I hope I'm not insulting you. I have many friends from Iowa, but flat, and or shall I say, the eastern side of Colorado, which is pretty flat too. And then, of course, you got the mountains, and but where it is mountainous is rather impressive, and on a scale even more impressive because the world is half the size of Earth. So, but we can clearly see the layers here in this area of the Euphrates Central Mountain Chain. So, and Adam, I know you're currently at your home in Colorado, so you get to look at the mountains, but you're not living in them, I presume.
Correct. I'm about 2 miles from the Front Range.
Well, it makes driving a little easier.
Yes, it does.
Especially now you've had this big snowstorm.
It also means less shoveling, with the exception of last weekend.
yeah, exactly. We've got just a moment or two. I would be, if anybody's watching this, I'll take you to a site that I'd seen pictures of it. Wanted to see it. It was targeted for stereo, and so they did the DTM analysis on it at University of Arizona, Al McEwen's team on HiRISE, and it's truly a remarkable feature. Basically, 3 mountains, sulfates, I guess gypsum mountains, light-toned sulfate mounds, and not quite as tall as the Grand Tetons, perhaps, but significant, especially in this area that's been scoured pretty flat. We see these nice sand dune fields as I come in close here, and we'll see just another beautiful nugget of landscape on Mars that I kind of feel like we're doing a little bit of service of doing early scouting for what will hopefully be national parks or solar system parks in the future. This is just, there are some of these places that are just remind me of our national parks in beauty. So thanks to MRO's mapping orbit is about the illumination of about sort of 3 in the afternoon lighting and get beautiful shadow detail. And coming up on this one, which is the innermost canyon facing mound, is that we can clearly see this beautiful aerodynamic dune formed by the prevailing wind direction toward the lower part of the screen coming at it. And a feature that I looked at with Jeff Moore, my old former housemate. Jeff, you may know, is imaging team leader for New Horizons, but we did a dean lecture at California Academy of Sciences a couple of years ago at the Martian Planetarium, and so I flew for Jeff, and so we kind of measured this feature. If I come around this side, it's a beautiful sculpting of this feature, but it really sort of reminds one of kind of Half Dome in a way. So welcome to the Martian Half Dome here, and it is about the right scale. This is just, you can explore to your heart's content. As I mentioned, we have these high-rise image and elevation maps. They were basically scraped from the high-rise site about a year ago. There are new additions, but we can add those in. This is a GDAL-based globe browsing system, so we can really take in any global maps, geotiffs, bring them in, and provide local patches, if not a already prepared global database like we've been looking at here. Our servers are a combination of, we use Esri for our high resolution Earth, and then Mars for the most part. But for our daily data of Earth, we're using NASA's Global Imagery Browse service. And then we have servers for the OpenSpace, other maps, and so on that are on servers at the University of Utah and your site at Linköping University in Sweden. If you're interested in the software, download it for free. OpenSpaceProject.com. Mac, Windows, Linux supported. GitHub site, wiki for the academic papers, YouTube channel for some training. We'll be updating some of the tutorials soon, featuring perhaps myself. So if I haven't bored you enough today, I can bore you in the tutorials. But thank you for watching, if you have been, and it's always a pleasure to share, especially with this conference. We've been using OpenSpace as a platform to at the Museum of Natural History and others. The California Academy of Science is doing this every week to invite scientists in, and we use OpenSpace as a platform to highlight their science, your science. So I'm just going to turn the stars back on before I head out of Dodge. There we go. Pull out. I'll put the satellite trails back on. I didn't show any mission visualization, but we do that as well. So, signing off.
I think we'll wrap up. I just wanted to say a very special thank you to you for taking the time every day to do these live tours with us. We very much appreciate it. For those that have joined us, you can visit www.openspaceproject.com. There's lots of information on there. There's the ability to download for both Windows and Mac. There's awesome tutorial videos on there. And I can tell you firsthand, as being somebody who's new to these types of applications, that those tutorial videos will definitely get you started. And a lot of our planetariums here that are clients of the Illuminati are utilizing OpenSpace in their domes and absolutely just love the visualizations. And of course, what's not to love about free 99? So if any of you guys have questions, feel free to shoot me an email at adam@illuminati.com. Otherwise, visit openspaceproject.com for additional information, and we look forward to seeing all of you again next year.
Thank you.
All right, Carter, have a great day.
You too.